Hey, Math 1030, it's lesson 9B, linear modeling. So in this section, we'll focus on functions, but this time we're kind of focusing more on the equations, and we're also just focusing on linear functions, not the whole world of different function types, just linear. So here's our kind of definition for linear functions. A linear function has a constant rate of change. That's important for one of your homework questions. And it will have a straight line graph. For all linear functions, the rate of change is the slope of the graph. And we can write linear functions in slope-intercept form, which is right here, y equals mx plus b. I'm actually going to write, as we go through this lesson, I'm going to actually not be writing the equations in that form. And so let me, while I have that equation up here, tell you that I'm going to focus on writing the equations like this. Because in context, that often makes a lot more sense, where the b is our starting value or our initial value. And then this other term represents how it's changing. So it would be the rate of change, which is m, multiplied by the the independent variable, which when we are working with these equations, most of the time we will use the independent variable t instead of the independent variable x. So anyway, so one of your equations or one of your questions on your homework, though, is going to have you identify these three elements of the definition of a linear function. Now, a linear function that has a greater rate of change is going to have a steeper slope, and a linear equation or a linear function that has a smaller rate of change is going to have a shallower graph or a shallower slope. So greater rate of change is steeper, smaller rate of change is, shallower. And then also you can have a negative rate of change, and those are the ones that are going downward instead of upward. Rate of change, ROC. Okay, we can calculate the rate of change by finding the slope between any 2 points on the graph, and the rate of change would be equal to the change in the y value divided by the change in the x value. And most of the time when we talk about rate of change, we use the variable m. So we're going to start with the rate of change, and then we'll get into writing some equations. So consider this graph. In words, describe the function that's shown, and then find the slope of the graph and express it as a rate of change. Don't forget the units. Okay, so if we were describing this in words, what it's showing me is that as the price of the pineapples increases, and let's look at our y-axis. It's the demand. So as we have the price of the pineapple increasing, that demand is going down. On your homework, most of these will be multiple choice. So we need to find the slope of the graph. Well, if we think about slope as the change in the y variable divided by the change in the x variable. On this graph, the change in the y variable, and even though it has a couple of points marked on the graph, I'm going to just go ahead and use the intercepts because those are probably the easiest 2 points to use. It's the demand started out at 100 and it went down to 0. So the demand changed negative 100 pineapples. And then we need to divide that negative 100 pineapples down 100 pineapples by the change in the x variable. So it changed from 0 to 10. So $10. And that x-axis is dollars. So if we simplify that, negative 100, and you can probably do this one in your head, but I'm going to type it in because sometimes you'll need to. That's negative 10 pineapples per dollar. And so that's the rate of change of our function. Okay, so skipping example 2 because I just realized today that they don't have graphs that you have to draw anymore on the homework. So we'll skip right to example 3. The following situation involves a rate of change that is constant, so it means it's linear. Write a statement that describes how one variable varies with respect to the other. Give the rate of change numerically with units and answer the question. So your driverless car maintains a constant speed of 63 miles per hour along the highway. So our rate of change, I think you'll be choosing from a little drop-down menu for each of these blanks. So first you'll put the dependent variable. So the distance traveled in this case is our dependent variable, varies with respect to time, the independent variable, with a rate of change of 63 miles per hour. And you will have to be choosing the units, I believe. So our follow-up questions are, how far do you travel in an hour and a half or 1.5 hours? And then how far do you travel in 3.8 hours? So if we have a rate of change of 63 miles per hour and we are driving for 1.5 hours, we just multiply that together. And if you think back to unit analysis, you can just think about that the hours there are canceling out, leaving us with a distance of how far we traveled. So it's just 63 multiplied by 1.5, which gives us 94.5 miles traveled. And then for the second follow-up question, 3.8 hours, we would just follow that same pattern. 63 miles per hour is our speed. Multiply that by 3.8 hours, and we get, 239.4 miles. And just watch the, excuse me, the rounding statements in MyMathLab so that you get the right number of decimals on these answers. Okay, example 4. Now from here on out, the computer, when you're doing your homework, will be asking you to write equations to model these different situations. So what we're going to have to do, first of all, is we're probably not going to be using x and y. In most cases, the computer is going to tell you which variables to use. I think on almost all of them, the independent variable is time t, but I think there might have been one on the homework where the independent variable was an n for number of tickets sold. So just pay attention to the computer. It will tell you what it wants you to do. And then, like I said earlier, we're going to use the equation, not y equals mx plus b like you're maybe used to, but more like y equals start value plus rate of change multiplied by, in most cases, a t. So for this one, we have a pet dog weighed 5.5 pounds at birth. So that's our sort of start value for this dog. And 2 years later, the dog weighed 20.5 pounds. Based on that information, we want to find a linear function to describe how the weight varies with age, and then use that function to predict the dog's weight at 5 and 10 years of age. So the first thing we need to do is we need to figure out the rate of change for this. So our independent variable is going to be the time or the age in years. So we're going to use a t for that. And then the dependent variable is the weight of the dog. And so I'm going to use a w for that. So we're going to write an equation for weight. So it's going to be w equals something. Definitely we're going to start with that start value in our equation. So it's going to be w is, the puppy weighs 5.5 pounds to start, plus, and now we need our rate of change. So the rate of change here, we have to think about how much the y value changed, or in other words, how much the weight changed, and then divide it by the change in time. So it looks like the dog started at 5.5 and then went up to 20.5. So that increase in weight, the change in the weight of the dog was 15 pounds. And that was over the course of 2 years later. So that gives me a rate of change of 15 divided by 2, which is 7.5. So plus 7.5, and we multiply that by the number of years. So that's our function, 5.5 plus 7.5t. The predicted weight at 5 years of age would be 5.5 plus 7.5 times 5. So we're just putting in 5 for the number of years. And that would be 43 pounds. And then if we predict the weight at 10 years of age, that would be 5.5 plus 7.5 times 10 years, which is 80.5 pounds. The last thing it'll do is it'll have a multiple choice section where you have to comment on whether or not you think that this model is reasonable. So in this case, it's probably not reasonable. We don't gain weight in a linear manner, neither do dogs. Dogs will grow really fast at first, then the rate slows down. Sometimes there's like a growth spurt in adolescence. I don't know if dogs do that or just people. But then growth pretty much levels off to 0 by the time the dog reaches adulthood. And then, I mean, it's possible that the dog will gain weight because it's overeating, but it's pretty much just not linear the way that animals grow. So that would be a not reasonable model. Let's look at another one. Suppose your job is to oversee an automated assembly line that manufactures computer chips. You arrive at work one day and find a stock of 135 chips that were produced during the night. So when you arrive, there's 135 chips. That is our starting value. We'll use that in a second. Chips are produced at a constant rate of 9 chips per hour. Create a linear function to describe the stock of chips at any particular time during your shift, and then we'll make some predictions. So the independent variable here is, once again, time, and we're going to use the variable t. This is probably going to be measured in hours, it looks like, because it's 9 chips per hour. The dependent variable here would be the number of chips, number of computer chips. So in this case, we don't need to do a calculation for the rate because it gave us the rate of 9 chips per hour straight up. So we can go ahead and just write the equation here. I'm going to use n for the number of chips. So n is equal to our starting amount, 135, plus our rate of change is 9, and we multiply that by the time. So the time into your shift at which there are 189 chips produced is what we want to answer. Oops, sorry. So this is a number of chips, and we're trying to figure out what time that happens at. So this gets substituted for n in our equation. 189 is equal to 135 plus 9t. We want to solve for t because we're wondering what time. So we would subtract the 135. 189 minus 135 is 54, is equal to 9t, and then we can just divide by 9 to get our answer. That t is equal to 6 hours. So 6 hours into your shift, you have a pile, I don't know, you probably don't pile them up, but a stack of 189 computer chips. Okay, is this model reasonable? You know, this one probably is reasonable. It's an automated system. It probably works just at a really steady and constant pace. So definitely this would be a reasonable model. All right, example 6. You can rent time on a computer at a local copy center for a $5 setup charge and an additional $5 for every 20 minutes. How much time can you rent for $32? So again, our independent variable here is time, in minutes this time. I missed a letter. Oh well. And we're going to use the variable t for that. And then the dependent variable is going to be the cost of the rental. So I'm going to use a C for that, and that will be measured in dollars. So the $5 setup charge, that's our initial amount. And so that will go in our equation. And we're going to have to do some calculations for our rate of change. The rate of change here is the change in our y value, or the change in our dependent variable. So it's a $5 charge per 20 minutes. And we divide it by the independent variable. So if we go ahead and divide that, $5 divided by 20 minutes, that gives us a rate of change of 25 cents, or a quarter of a dollar per minute. So if we are writing our equation, that cost is going to equal the $5 initial starting fee plus 25 cents per minute. So there's our equation, $5 plus 25 cents per minute. So our question that we want to answer as a follow-up is, how many minutes can we rent for $32? Well, $32 is a C value, a cost. So our equation is going to be 32 is equal to 5 plus 0.25t. So we're going to subtract the 5 as we solve for the time. And we get 27 is equal to 0.25t. We can divide both sides of our equation by 0.25. Whoops. 27 divided by 0.25. And we get that the time that we can use for that $32 cost is 108 minutes. Is this model reasonable? Yeah, it's pretty reasonable. It used to be pretty common for computer usage to be charged this way. Pretty much not as common anymore, just because more people have their own computers. But you used to be able to go to different copy centers and rent computer time. So this is a reasonable model. All right, I have two bonus examples that are not on your notes, but this first one I am including right here because it's a negative rate of change, and I feel like none of my examples had a negative rate of change, so I just wanted to go over one with you. You'll recognize it, I think, as homework problem number 12. And then another bonus example is this one involving degrees Fahrenheit and degrees Celsius, because I think the wording is weird, and I think a lot of you will be asking me for help on this one, so I just thought I would include it in the video. So first, this negative rate of change one. We have a $770 washing machine, so that's going to be our starting value. And it is depreciating at a rate of $70 per year. So our rate of change is not positive 70, but negative $70 per year, because depreciating means that the value is going down. So the rate of change is negative $70 per year. All right, so we want to find a function for the depreciated value of the washing machine as it varies with time. And then our follow-up question is, when does the depreciated value reach 0? So our equation is going to be, and they're telling me to use V for value, I guess. So the value of the washing machine is, we want to use our starting value. Whoops, I missed a 7. The starting value was 770. And then we have the rate of change, and it's going to be minus, because it's that negative rate of change, 70, and it says using t as the variable, 70t. So that would be our equation. That's the first part. And then the second part, the follow-up question is, how many years will it take until the machine has depreciated to $0? So that's a value, so we're going to put that in for V and solve. In this case, personally, I'd probably add 70t, but you could do other ways. So we have 70t equals 770, and then we can divide by 70. And that will cancel out, and we get t is equal to 11. And maybe you could do that in your head. So 11 years would be the time till it depreciates to a value of 0. All right, so that was your first bonus example. Second bonus example, the wording on this is weird. It says a 1 degree change on the Celsius temperature scale is equivalent to a 9/5 degree change on the Fahrenheit temperature scale. And we want to know, how much does the Fahrenheit temperature increase if the Celsius temperature increases by 2 degrees? So first we have a little multiple choice, which statement is correct here. So we know that a 9/5 degree change in Fahrenheit is equivalent to a 1 degree change in Celsius. So 9/5 of a degree Fahrenheit is the same as a 1 degree change in Celsius. So this is a 9/5 Fahrenheit degree change per Celsius degree. So that is on our choices here. The Fahrenheit temperature varies with respect to Celsius with a rate of 9/5 per degree Celsius. It's choice A right there. Very tricky wording. So you have to have, yeah, anyway, That's why I'm doing this, because the wording is so weird. And then our follow-up question, I'm just going to do the first, but I think you'll have two on your homework question. So it says, what is the increase in Fahrenheit temperature if the Celsius increase is 2 degrees? So our rate of change is 9/5 of a Fahrenheit degree per degree Celsius, and we just multiply that by the 2 degrees Celsius that it gives us, and the units degrees Celsius cancels out, which gives us our degree Fahrenheit answer. So it's 9/5 of a Fahrenheit degree, and we multiply that by the given temperature, 2 degrees. So that would be 3.6 degrees Fahrenheit. And you could have inputted that as a fraction, 9/5 times 2. I just sometimes forget to use that fraction button. And then if you want a decimal answer, it's almost faster to just type it in as division so you don't have to convert it. Anyway, 3.6. The other, I'll go ahead and do the second part. It says if it was a 27 degrees Celsius change, well, we would take that 9/5 rate and multiply it by 27 degrees Celsius. Again, the degrees Celsius unit cancels out. So 9/5 being multiplied by 27 gives us 48.6 degrees Fahrenheit. So, all right, that's it. That's 9B. Let me know if you have any questions that come up. I'm more than happy to help. Thanks.